Hello. Hello.
Good afternoon, Dr. Francis.
Doctor.
Yeah, good afternoon. How are you guys?
Very well, thank God. How are you doing too?
Fine, good. All right. Today I may not stay long with you guys, but I've noticed that although we are dealing with machine learning, isn't it? Because sometimes before we get into the Python aspect, it seems that most of us are not so clear with most of the algorithms. Is that right? Or do you understand the algorithms? Yeah.
Not fully, sir.
Not much.
Not fully, right? Because I've noticed that because it's very easy to use the code, but it's for you to understand what's happening behind that algorithm. Okay. So what we'll do today, I will try and just go through some of them for you guys, so that at least you have an understanding of what it is. Okay, because you know the end product of all these things that you are learning is to try to build an AI, an artificial intelligence, isn't it? But you see, behind the AI is your machine learning. Because under your machine learning, remember, because when you say AI, what does AI mean? When you say artificial intelligence, what does that mean? Artificial intelligence. When we say artificial intelligence, what does it mean?
It's a program that works exactly like a human being.
Exactly like a human being, is it not?
Yes, sir.
You know, like human beings learn from experience, isn't it?
Autonomous.
Yes, human beings learn from experience. But computers or machines, they follow instructions that is designed by the human being, isn't it? So we're not trying to see what if we as human beings are training the machine to now learn, hence the name machine learning. Can you see that? So machine learning is just a branch of AI. It's a branch of what? AI. Okay, and what does it do? It just the use of computer was to perform tasks which requires human intelligence, such as decision making. Because ultimately, what we want to do, we want to what? Delegate decision making. But the truth is that you cannot fully delegate decision making to machines. Okay, but those decisions that are routine, every time is routine, you can what? Delegate it to machines. But the part that leads to emotions, that has to do with emotions, you cannot delegate that part to machines. So we have to also be careful with that. Because that's why we say for the ethical aspect of it, right? Because there's still ethics in machine learning. Okay, so it's not everything that has to do with emotions, you cannot fully what delegate it. So what we ultimately do is those routine tasks that we need to start making decisions on is what we delegate to machines. Okay, so there are certain things that we can look at, decision making to some extent, right? Visual, so to see some things, for example, you can see an x-ray from a hospital, isn't it? You can detect whether it has cancer or not cancer from your Google Maps, from voice, is it not? From maps, all those are visual and voice recognition. Those are what? AI. So what machine learning is about is just simply a general term, is it not? When the computer learns from what? Data. So data is the critical aspect of it, data. So you must have what? The data. Okay, you must have what? The data. But again, what you will notice is that what we have been doing before in your basic programming, so we learn from what? Data, isn't it? You know that in traditional programming, what happens for you to arrive at this decision, you know, like in Excel, we'll say if this is greater than this, give this, else this, is it not? So there's a rule to it. So how we program normally is that we have what? Our rules. We know the rules, is it not? We'll give it an answer. Say, okay, this is the answer. We'll say this is your what? Answer. Based on this answer, yeah. Based on this answer, in fact, before the answer will even come, you need to give it data. You will give it data for your traditional programming is not even answer. You give it data. You give it what? Data. Sorry. Okay, let me do it again. So you give it the rules. So those rules, like you have in Excel, you give it data. Okay, based on that data, it now comes up with an answer. Is that not how we do it in Excel? You know how we do it in Excel?
Yes, sir.
Because this is generally your traditional programming. Okay, this is how you do it in traditional programming. But you see, in machine learning, it's a little bit different. What we do is that we give it the answer. We'll give you the answer first. Say, see the answer. Oh, this is what I want you to always bring out from me. Give you the data. Can you see that? Give you the data. Based on this data, come up with your own rule. Can you see that? Come up with your own what? Rule. This is what machine what? It's like an inverse of it. So what it does is that it doesn't wait for you to program. Automatically, it will pick it on its own. So that anytime you bring a new data, it already knows the rule and will figure out the answer for you. Do you understand that now? So when you are going into machine learning now, you must also understand that how do I know the kind of algorithm I'm going to use? Okay, it depends on a whole lot of things. Okay, it depends on a whole lot of things. But what you need to understand is that machine learning learns from more data. Human beings learn from experience. Machine learns from what? Data. Okay, so that is why when you are choosing your machine learning algorithm, the first thing you must understand is what is the type of problem. What is the type of what problem? What do you say are the major problems? The kind of problem we use machine learning to solve. So ask what kind of problem is it? We say is it a regression problem? Exactly. Is it a regression problem, or is it what? A classification what problem? How do you know a regression problem? How do we know a regression problem?
Using the target variable.
Yes, using a target. So you look at your model y as a function of x. Okay, y as a function of what? X. This is our target variable, isn't it? So we are seeing once this is our target, these are our what? Feature. These are our what? Features. Okay. So how do I know what? Once this is my target variable, contains numbers, continuous numbers. It can be 1, it can be 2, it can be 2.5, it can be 10. As long as I'm going to predict what? A continuous data, isn't it? Then that gives us what? Regression. But where what we are trying to target, our target now becomes 1 or 0. Can you see that? We are now doing some form of what? Classification. Is that clear? Is that clear?
Yes, sir.
All right.
Yes, sir.
Now, you see, when you are so we have said that one thing you consider when you are choosing your algorithm, one of them is what? The kind of problem is it is, isn't it? Whether it's a regression problem or classification problem. Now, another thing we must also consider is the size of the data, the training data sets. The size of the training data sets. There are some algorithms that work with small data sets, some work with large data sets. Okay, for example, things like NaIFS-B, KNN, they work with what? Smaller what? Data sets. Another thing you are going to also consider is the accuracy of the algorithm. Some are more accurate than the other. But remember, with the no free lunch theory, which says that what? There are so many theories, isn't it? But what we are going to do is to choose what? Which one are we choosing? Which one do we choose?
The most accurate.
Yes, that there's no one particular theory to solve every problem. Okay, but what we are going to do, we are going to pick the one with the most what? Accurate what result. So accuracy is what you must consider. And that thing you must consider is the time to train the data. You know, there are some machine learning algorithms, especially on live data set that are so large. Do you know there are some can take you 2 days to train? You know, when we were running regression and logistic, you saw that it was 1 second. I think we noticed that when we ran it, we say we are training. It took us like 1 second, isn't it?
Yes, sir.
There are some will take you 2 days to train. 2 days. As is training, what you are training, that's your train test set that you just do. And we'll just go and do prediction. It doesn't work like that. So some can take you 2-3 days. It's training. Just imagine after 2-3 days, after the 3rd day, that gives you error. Imagine what will happen. You know, like the one we have been doing. If you see error there, at least you can treat it now, is it not? So imagine it took you 2-3 days before it brought out that error for you. So how frustrating that it can be. Okay. So sometimes you must consider what the time of our training data. Some are more faster than the other. Okay. Then another thing we need to take into consideration the number of parameters. What do you mean by the number of parameters? What do you understand by number of parameters?
The feature. How many features?
Okay, yes, features can be part of it. Yes, number of features can be there. Yes, number of features, because remember, the larger your feature, right? Yes, the more accurate, but sometimes it can take you longer time. Because another thing again, you must understand that sometimes these features may not be explainable, or they may be accurate but not explainable. Okay, because sometimes you cannot see that practical relationship, but you say, ah, this feature explains it very well. But practically, it makes no what meaning. So you must take into consideration the features and explainability. Is that clear? Do we get that? Okay. So what we are simply saying is that machine learning focus on the use of data, isn't it? An algorithm. So anytime you say, I am building my model, anytime you say, I am building my model, what are you simply saying? We say, I am building my model. Your model is made up of what? 2 things. What are they? Your data and what?
An algorithm.
An algorithm. So if I say I am training data, the data, you are talking about what? You are training your model, you are talking about the data and what? The algorithm. Is that clear? So if I say
Yes,
model,
sir.
you are talking about what? Your data and
Data
what?
and algorithm.
Exactly. Okay. So if we say we are talking about machine learning proper, right? Machine learning proper. So remember, there are 3 aspects to it, isn't it? We are talking about supervised what? Machine learning, unsupervised machine learning, isn't it? And there's another part called reinforcement learning. This reinforcement learning is actually your deep learning. It's actually your what? Deep what? Learning. But these are the 2 we focus on. Okay. All right. So we know that for supervised learning is broken into 2 parts, isn't it? What are they? You have what? Regression. Is it what? We have what? Regression. And we have what again? Classification. We have regression and we have what? Classification. Okay, and you have what? Classification. This my mouse. Okay, we have classification. Okay, I think we remember this one now. Because this is the one we focus on actually. Okay, much later we'll come and deal with this one, but let us focus on this one first. So you see, for regression generally, in fact, sometimes in practice you will hear what they talk about CAT. Have you heard of CAT? C-A-R-T. This is called what? CAT means classification and what? Regression tree. It's like decision tree, but using what? Regression. So it's called classification and regression tree. Because you see that in that your regression, okay, most times where I have y is a function of what? X. Okay. If I was to write it in full, it means that y is what? Beta naught, is it not? Plus what? Plus what? Beta 1x. Isn't it? This is a simple model, is it not?
Yes.
This is a simple model, okay? Now remember, this y is your target, is it not? This y is your target, okay? Why this x is your what? Features, okay? Is your what? Features. So we are trying to use these features to what? Predict this guy, is it not? So for us to know that it's a regression problem, how do we know it's a regression problem? You said?
The y is continuous.
The y is continuous, exactly. The y is what? Continuous, okay? Y for classification, the y is what?
It's finite, 1 or 0.
Is category, they call it categorical. They call it categorical. For regression, it's called continuous, or for classification, it's called categorical. It's called categorical. Okay. Why for this one is called what? Continuous. Because when you are teaching it in terms of machine learning, the way we teach it is a little bit different from when we teach how it's in statistics. But it's the same knowledge you are using. Okay. Now let's start with regression first. Now you see this regression. The regression we have been working with is what? Linear. Is it not? Linear regression. The regression we have been working with is what? Linear what? Regression. Now, but you see, the same way we classify supervised machine learning as regression and classification, some other people, they classify it into two. They can classify it into linear models. They can classify it into what? Linear models. And they can classify it into tree-based models. You can call it tree-based models. You know when they say tree-based, it means you are talking about regression tree. So which one are we familiar with now? We are familiar with regression and classification, isn't it? Which one are you classifying? Okay, regression. Okay, so let's finish with regression classification. Okay. Now you see, under regression, we are talking about linear regression model. But you see, under this again, under this regression, you have another type of regression. Okay. You have the one they call ridge regression. You hear of ridge regression, and you have another one called lasso regression. Have you heard of these ones before? Have you heard of this one before?
No.
Ridge and lasso. Okay.
Yeah.
They're called ridge and lasso regression. Okay. But you see, for your classification, you have quite a lot. For regression, you have quite a lot. Okay. One of the common ones is what? Your logistic. I'm sure this one we are familiar with logistic, isn't it? You have your logistic regression. Okay. Now, some other ones you have, some other popular ones you have what they call naive Bayes. Naive Bayes. You know, to run it in Python, you know they are very easy to run in Python, right? You have KNN. You have KNN, K nearest neighbor. You have another one. Is it a support vector machine? SVM. It's called SVM, support vector machine. Okay. Another one you now have is called decision tree. You now have what? Decision tree. In addition to this decision tree, now you have another one they can call random forest. Called random forest. I'm sure we have heard of this, some of these algorithms before now.
Yes, sir.
From you, sir.
Yes, sir.
From me. So it should not be from you. By now, you guys should start reading them on your own. Okay? You have what they call random forest. Okay? But you see that in this random forest that you are doing, there are other aspects you also need to understand. Because this random forest uses what they use what they call, there's something they call ensemble. Have you heard of ensemble before? Ensemble. Have you heard of ensemble?
No, sir.
Ensemble is just like, you know, like you say assemble. When you say assembly, what does assembly mean? To assemble.
Putting the parts together.
Exactly, exactly. So ensemble simply means combining different models together. It simply means what? Combining different models together. So there are two types. There's what they call bagging method. There's what they call bagging method. Okay. Then there's another one they call a bootstrapping. Have you heard of bootstrapping before?
Yes, sir.
Yes, sir.
Yes.
Bootstrapping.
Computing.
Bootstrapping. So they use two methods. So this assembly method use two methods. One is bagging method and what? Bootstrapping. So you see, part of this bagging method is what? Your random forest. Okay, so your random forest uses what? Bagging method. But your bootstrapping method, either you use some of the algorithms you have under this. You will hear of gradient boost. Have you heard of gradient boost? Gradient boost. If you go through most of this cargo, you will see them there. Gradient boost. You have another one they call, which other one they call? XG boost. Extreme gradient boost. So gradient boost. You have another one, light boost. There's one they call light boost. You see, they have quite a lot. Light what? Boost. There's even another one you call ADA boost. You know what ADA boost means? ADA boost, adaptive. So when you are learning machine learning, can you see just this supervised learning? How many algorithms have you seen now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And it can be more than this. So when you say you are learning supervised machine learning, at least minimum, you must learn this 14. Minimum. Do you understand that? So this is just supervised machine. You have not even talked about unsupervised. So let's first of all learn supervised. But this is an end-to-end, how you need to understand it. So anytime you are dealing with classification, you are going to run as many of these ones as possible. Then what do you now do? From all of them, which one do you choose from? From all these methods, the most accurate, because they are all what? Classification. All of them here, they are all what? Classification. So that is why in practice, this is what you are going to be beating, classification. So that is why it's also important for you to what? Be exposed to as many what? Algorithms as possible. Are we clear with this? Are we clear with this?
Yes, sir.
All right, good. So what
Yes,
I want
sir.
to do, yes.
So I just have a small question.
Okay,
So
yes.
in the ones we've been doing before now, that's the ones we did like 2 weeks ago, 3 weeks ago.
Yes.
We always came up with we came up with, after we did the logistic, when we do the regression, we always came up with a figure and it gave us a percentage and all that.
Yes.
What do you do when the features you chose, you can't really explain them, as they give you a high figure, but you can't really explain how the result came about? Like, for example, maybe they are looking for, like Titanic now survived, and
Yes.
then you use ticket number, for example, and then ticket number is now an accurate thing, but you can't really explain how ticket number tells you whether that's alive. Do you drop that feature even though it's giving you an accurate?
Okay, you drop it. So you remember what we said, that what are those factors we consider? We said explainability. That means there must be relation, because understand the essence of all these things. The end goal of this is for you to what? Make decisions, isn't it? To make decisions. But you see, you must be able to explain how that relationship is affecting your prediction. It's just like saying, oh, that Titanic survived and not survived. Is it not survived and not survived? And you now brought a new variable about fish. Is it not about fish? Isn't it? And this feature is explaining this very well, isn't it? But in reality, you cannot explain it. You know, that's the explainability we are talking about. So sometimes you can bring in variables, but they cannot explain it. That's why when we are doing your feature generation, you also have to be very careful, because sometimes it can be so complex, yet the accuracy is very high. But in terms of explaining the individual variables, you cannot do that. So you need to consider what? Explainability. So explainability in terms of it has practical meaning, practical interpretation. Do we get that?
Yes, sir.
All right, good. So just be careful with the number of variables you are putting there, so that you don't put so much that at the end of the day you cannot explain it. Okay, so let me explain this for you now. You know, for supervised learning, what makes it unique is that, you see, when you are training your machine, your model, this your target variable, is it not? It has what? Labels. So one thing about your supervised what is that there's what? The target has what? Labels. Is it not? And you label that data with the correct answer. Isn't it? So we make use of what? A labeled data. The data is labeled. That means we know our why. We label it. Oh, good, bad. Man, woman, true or false, fraud or not fraud. So that your data is labeled. So at the end of the day, what do? We make use of that labeled data set to what? Train the algorithm, either to classify in case of classification problem, or what? To predict the outcomes, in case of what? Regression. So what we are simply doing, we are mapping inputs to the output. This is the input, this is the output. This is the input, this is the output. That's what we do in supervised machine learning. So let's do the first one, which is the foundation of everything we are doing, your linear regression. So in this your linear regression, I'm sure you have been hearing of algorithms, is it not? You have been hearing of algorithms before, is it not?
Yes, sir.
Yes, sir.
So what do you understand by an algorithm? What do you understand by an algorithm?
It's like a set of instructions that helps you solve a particular problem.
Okay, instead of what? Instructions, isn't it?
Yeah.
Now, have you imagined what goes on behind the regression? Have you imagined what goes on behind the regression, the algorithm behind it? Have you ever seen what goes on behind a linear? You know, for example, you have that your equation. Y is equals to what? Let me do it here. Y is equals to what? BO, is it not? Plus B, let's say B1x. Is it not? Let's say plus your error term. Is that not true? Because remember, this is what is capturing the, if you have your points here, 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 you are drawing a line of best fit, isn't it? In such a way that you try to capture most of the lines on this, because going back into the data to look at the pattern, you show regression. When you say somebody is progressive, progressive means what? Progressive means what?
Moving forward.
Going forward. Regression means what?
Moving backward.
Moving backward. So you are going backward in the data to observe its behavior. And you summarize that behavior with this word equation. So it means your job is to try to ensure, because anything outside this line is an error. Anything outside this line is an error. Anything outside this line is also what? An error. So what do you want to see your error? Do you want to maximize your error or minimize your error?
Minimize.
Minimize, isn't it? So we want to try to reduce this error. That's the essence of what regression is doing. So it is predicting it with minimal what error. Do we understand that? Is that clear? So your linear
Yes, sir.
regression tries to predict what? Your linear regression tries to predict what? A what? Continuous what? Variable. Isn't it? That means this our y follows numbers. Can be 1, it can be 2, it can be 2.3. Okay. But another thing again we must understand is that sometimes you see that when you do your data, you will need to understand that in this regression, our objective is to try to be as accurate as possible. Okay. But in doing that, you must try to what? Minimize what? The error. So that is why some factors you must take into consideration is that what? You must have what? Low variance and low bias. There must be what? Low variance and what? So low variance means what? Minimal what? Error. You know what variance is now? Variance which are actually used to capture the error. So the difference between what you have on this line and what you have here is a variance, which is the error. So your objective is to what? Minimize this what? Error. Hence low variance. Is that clear? So what I will do now, I want to show you the algorithm behind it. Okay, because remember they tell you that for you to be a good data scientist, you know they will tell you there's an element of mathematics there. Is that not what we have said? That is
Yes,
an
sir.
element of mathematics.
True.
So let me just show you a bit of that mathematics that is behind it. It's just for you to understand when you hear an algorithm. So you say, okay, this is what was built behind that Python. That's your sklearn. So you understand what has gone behind it. So remember, what's our objective here? What's our objective here?
To determine the target.
Yes, we want to determine the target also by ensuring that what you minimize the error, because this is what you call your error term. This is called what? The error what term. So your objective is to what? Minimize this error. Do you agree with that? So have we seen that the objective to minimize this error? Are we okay with that?
Yes.
So if our objective is to minimize this error, so what do? We make this error the subject. So if error is subject, now what do we now do? If the error is subject, now what do we now do?
Y minus B.
Y.
Exactly. Y minus what?
B.
0. Is it not? Minus what?
Yeah.
B1.
BX.
Is it not? Is that what we do?
Yes.
Sir.
So what we are going to do, we want to now minimize the error, isn't it? We want to now minimize what? The error. And you know that to minimize the error, okay? Because you know sometimes when you are subtracting, it may be larger or smaller, isn't it? So to make it easier, what do you now do? You take the square. Because you know sometimes you have x minus x bar. You know, actually, this is what you have actually done. You are just subtracting the value from that mean or something, isn't it? So it may either be positive or negative. It can be positive or what? Negative, isn't it? But to ensure that it is always positive, what do you now do? You take the square of both sides. Okay? You take the square of what? Both sides. So if we are taking square of both sides, what do we now do? So take square. So if you take square of both sides, what do we do? So if we are taking square, what
It
do
will
we
be
do?
positive.
Yes, it will now be positive. So how do we do that now? If we are to take square of both sides now, take square of both sides. So what do we now do now? If we are taking square of both sides, what will it be? If I take square now, here will be what? U square. Is it?
U square is equal
Is
to y
equal
square.
to it's also just take
Y
all of them
square.
one. Just say y minus b0. Is it not? Minus what? b1
B1.
x. Is it not? All square. Does that make it easy for you? Does that not make it easy for you?
Yes.
So once you have squared both sides, you know, remember, because you are going to have a series of data. So most time they are going to be putting I there. I simply means there will be a list of data. So for example, that's your X. You can have 1, 2, 3, 4, 5. You see that? So by the time you subtract them, what do you now do? You have to add them up. You see that? You now add it up. Is that what we normally do? So after we take this square, we'll now sum it up. We'll now sum it up. So what do? We'll now sum it up. We now have summation u square and what is equals to summation what? Can you see that? Have we got this? Are we clear up to this point?
Yes, we're clear.
Now, because our objective is to minimize, is it not?
Yes, sir.
So, you know, in regression, we want to derive the value of A and the value of B, is it not? This is our intercept and this is our slope. We want to determine this value. Remember your regression we ran in Excel. You see intercept, you see a value there. You see the slope, you see the value there. Is that not what we do?
Yes.
Is that not what we have done?
Yeah.
Okay, good. So in that case, if we are to minimize it, and remember, when we are deriving, we're also trying to minimize this error. Can you see that? So we will minimize the error. So to minimize error, so what do we now do? The primary school, they taught us this one. To minimize, what do we do? If you want to minimize a equation, what do you do? So to minimize the error, what do you now do? Let's say with respect to B0. B0 is what? What is B0?
Intercept.
Intercept, you know. So we want to minimize the error with respect to the intercept. So to minimize the error, what do? We now do what? A differentiation. Can you see the mathematics you now did the machine learning? You now do use what? Differentiation. Was it primary school they taught us differentiation that time?
Secondary school.
That's not primary
Secondary
school.
school.
Secondary school.
Yes. Part
So
of
if you
other
had to
maths.
Exactly. So if you have to differentiate it, how do you differentiate it? You now be what? The what? The u square, is it not? All over what? The what? The B0, is it not? With respect to B what? 0. You know this change, you know what this change simply means? It just simply means X minus X bar. This is a change now. This is a change, is it not? But this is a partial change. So it's a partial change with respect to what? B0. So if we differentiate it, you know how it goes. This one will come and multiply this one. So we'll have what? 2 summation, isn't it? This one will remain there. I think this is how they taught us that year now. Y minus what? B0 minus what? B1 what? X. Okay. Now you see inside this bracket, do we have B0 there? Do we have B0 there?
Yes, sir.
Differentiate it. If you differentiate B0, what do you have? If you differentiate this B0, what do you have? Is there any change there to a constant? You change the constant. If you change the constant, it's still 1, is it not? So it will still be this one, it's still the same thing. So that's why we're going to have what? Minus 1. Okay. So what can we do? We can now multiply them together now. And remember, everything is set equals to what? 0. Okay. If we multiply it, so we now have minus what? 2 summation, isn't it? All of brackets y minus what? B0 B1x. Hey, they have come again. All these, they are nonsense. They have come again. Now imagine those things they are programming. At the back end is all these things you are seeing here. You see that code you are writing there? You see the code you are writing here? Fit the model, is it not? When you say x-train.fit or whatever data.fit, they put x-train, y-train. Do you remember that?
Yes.
So at the back end is all this mathematics you are seeing there. So what do they do now? To ensure this, I can divide both sides by minus what? 2. Divide here by what? Minus what? 2. So what do I have? This will go with this. When 2 goes 0, what do we have? It's still what? 0. So what are we left with? This multiplied by this, we have what? Summation y. Summation what? Y is equals to what? Or let's say, okay, minus what? Summation times a constant. So anytime you multiply a summation by a constant, what's that rule? Summation by a constant. It normally gives you what? N. It will give you what? N and the word constant. That is the rule. I don't know if you remember any engineer here to explain this thing for us. Is there any engineer here?
I'm here, sir.
Please, what is that rule that they tell us when summation goes over a constant?
Okay. Because you'll be getting the same number.
You will get the same number exactly. So you see, for example, but actually the mathematical rule is that when you have the summation of a constant, is it not? The summation of a constant starts from the first number. I equals to 1 to the last, ahead to the last. So if you take that summation, it will simply be what? Summation times what? The constant times the number. So that means if we have a constant of 5, if we have a constant of 5, is it not? And this is from 1 to 3, what will it now be? It is simply be what? 5 times
3.
5 times 3, exactly. 5 times, which will give us what? 15. So that's the rule there. Is the summation rule. So when the sum of a constant is equals to what? N times the constant. That is the rule. So that is why you have what? Summation times this constant to be N times what? The constant. Okay? Minus what? B1 summation X. B1 summation what? X. And everything is equals to what? 0. Now, if we take everything to the other side, so we are looking for what? Summation Y is equal to, this guy will cross, this guy will cross, this other guy will cross. So we now have what? NB0, is it not? Plus what? B1 summation what? X. Does this equation look familiar to you? Does it look familiar to you?
Yes.
If you go and check your regression equation, this is how they actually will derive them. So that means if I want to minimize with respect to, B1 now, so what do I do? With respect to B1, what do I do? I'll come back and differentiate it again. This is not going to be what? The summation U square all over what? B1. Okay, so if we differentiate it, what do we have now? Let's come back here. This is the original equation now. So this will multiply this in the same thing, is it not? 2 summation, open bracket. What do we have? This same constant will remain inside. Y minus what? B0 minus what? B1x. Is it not? Then we'll differentiate this x inside. So if we differentiate this x inside, what do we have? If we differentiate x inside, what do we have? If we differentiate, sorry, it's B1 we are differentiating. If we differentiate this B1, what do we have? It's minus 1, isn't it?
Minus 1. Yeah.
Minus 1. So minus 1 times x is what? Is what?
Minus x.
Minus what? X. Is it not? You have what? Minus what? X. Equal to what? 0. So what do we do again? We multiply this by this. So what do we have? We have minus what? 2 summation what? X. Can we see that? Can we see that? So we now have y minus what? B0 minus what? B1x equal to what? 0. So what can we do? We divide both sides by what? -2. Divide both sides by what? -2. So what are we left with? This guy is equal with this guy. This guy is equals to what? 0. Is that it? Is that it?
Yes,
Good.
sir.
So let us expand the bracket now. So expand this bracket now. So what do we have? So we have summation what? X, Y. You know, minus what?
Summation x b0.
B0 summation X. Good. Yes. Then what do you
Minus
have again?
b1 summation s squared. S squared.
B1 summation what?
X squared.
X squared. Beautiful. And everything is equals to what?
0.
0. So we are looking for this. So we leave it. So we leave it here. Summation xy is equals to what now? Is equals to
B0 x1
B0
So
x
b0 summation x
summation x plus what?
b1 summation
B1.
s squared.
Summation what?
S squared.
X squared.
squared.
Beautiful. So remember, this is our equation 1. This is equation 1. This is what? Equation what? 2. So let's bring it together. So your equation 1 is what? Summation xy. So if you go and check most of your statistics textbook, have you seen this formula before?
Yes, sir.
Have you seen this formula before? So this is an example of an algorithm. Can you see that? It all boils down from mathematics. So it is your understanding of an algorithm that you now use it to build that program, all those codes you are now building. So this is now what summation what? This one is summation y. Sorry, this is summation y. That's summation y. This is summation y, and this summation what? Xy is equals to what? B0 summation what? X plus what? B1
summation x
what?
squared.
X squared. This is equation 2, is it not? So remember, our objective is to look for what? B0 and what? The slope. Is it not the
One.
intercept and what?
B1.
The slope. Please take note. Remember, this is a simple regression. Though. This is simple regression. So imagine multiple regression. You can now have x1, x2, x3 to whatever number you have. So what are we looking for? We are looking for what? B0 and B1, is it not? So what we normally do, we can use a matrix to solve it. Remember your NumPy. Do you remember your NumPy?
Yes, sir.
So that NumPy is the matrix part we are now going to be handling here. So this is the NumPy. So here we have B0, B0 here. So B0 can come out from here. Here we have B1, B1. B1 can come out from here. Okay. So let's bring the equation out. So we have summation what? Y. Summation what? XY, isn't it? Then this is 1. Is equals to, we are putting the matrix form. Is equals to what? When B0 come out from here, we are left with what? N, isn't it? When B0 comes out from here, we are left with what? Summation what?
Summation x.
X, good, isn't it? So because this is not a matrix. When B1 comes out from here, we are left with what?
Summation x.
X, exactly. And when B1 comes out from here, we are left with what?
Summation x.
Summation what? The same summation X now, isn't it?
Yes, sir.
Is it the same summation X?
I think that should that
Okay,
be
this is
S square.
S square.
S square. Aha, it should be S square.
Yes. So here will be what? Summation what?
S square.
S square. Beautiful. Okay. Now, what we are looking for now is what? B0 and what? B0 and what? B1. Now, that NumPy you have been doing since, that NumPy, can you see this way NumPy now comes? Because remember, in coding, when we are working with tables, we were working with tables. That's how we understand it in Excel. But in programming and mathematics, we don't understand it like that. So what do? We use matrix. But all these things are your variables. All these things are your what? Variables. Okay. So can I wipe off this side? Can I wipe off this side?
Yes, sir.
All right, let me wipe off this side. So you understand where we are going to. So imagine those codes you are doing. This is what is happening at the back end. This is the mathematics at the back end. But you see, when we write the code there, you just be like, this is just solving for us. But forgetting that there's a whole lot of mathematics behind it. That is why we say.
Excuse me, sir.
Yes, please.
The assumption of the B1, that's the differentiation of B1, where you take it as X. That's where I didn't get the negative.
Okay,
X.
here, right? You know, it's like a change, is it not? B1 is like a change, is it not? So
the other
B1,
side, the B1, I think is the one that is negative X1.
Yes, this one now, is it not? By the time you differentiate this now, is it not? What you have is 1. If you differentiate this one, B1 is 1 now.
Yes.
It's 1. 1 times X. You know this X is multiplying this. You know this one, there was nothing multiplying it before. So it was just 1.
Yes, sir.
But this one was 1. So it was 1 times X. That's why you have minus X.
Okay, sir.
You see it here. It is minus B0, B1X. So by the time you differentiate this now, minus 1X. Minus 1 times X is minus X.
Yes, sir.
And so I had got it there. Okay. So let's look at this last part. Now, when we are doing it, you remember in the matrix, we call this one what? The determinant, isn't it? So if we are finding the determinant of this, what we have had? We have had what? Summation what? X squared, isn't it? Minus what? Summation X all square. Okay, minus summation X all square. So this is what we are going to be using now as the determinant. So which means if I'm looking for B0 now, so this will be our B0. So anytime I'm looking for B0, anytime I'm looking for B1, okay? If I'm looking for B0, what do? I will take this value, put it here. If I'm looking for B1, what do? I'll take this value and put it here. Can we see that? So that is your matrix determinant. For those of us who still remember it. So if I'm looking for B1 now, what do? Then I will divide it by this determinant here. Okay. So if I'm looking for B1 now, what B0, what do now? It will be what? B0 will be equals to what? B0 will be equals to what? Summation Y. Summation what? XY. Isn't it? Then this one, we'll leave this one the way it is. Summation what? X. Summation what? X squared. Can you see that? All over our determinant. Can you see our determinant here? This is what? N summation X squared minus what? Summation X all squared. So if I bring it in your normal formula, what do we have? Here will be what? Summation Y summation X squared minus what? Summation X, is it not? Summation what? X, Y. All over what? N summation what? X squared.
X.
Do you know that? You know this one also resembles your correlation formula?
Yes, sir. Somehow.
Somehow, isn't it? Exactly. This is your what? B0. This is your what? B0. That is the value of your A. To get B1 now, what do we do? To get B1 now, what do we do? So B1, this guy will remain the same, isn't it? So we have what? N what? Summation X. Y, so this guy is B0 here, this one. B1 will now replace this one now with it. So we now have what? summation what? Y, summation what? X what? Y. Okay. All over what? This determinant, is it not? N summation x squared minus summation x. Good. Now, if we break this one further, what do we have now? N summation what? xy. Is that not it? Minus what? Summation x,
Summation X, summation Y.
y, isn't it? All over what?
N
N
summation X squared
yeah, minus what?
EX.
This one, is it x squared? Is it also x squared?
Yes, it's X squared.
Z squared, okay, yes, all squared. All squared, okay, good. So go and check your formulas normally, your regression formula. Have you seen the regression now? So this is the value that you now use to get your P, and this is what you are going to use to get your A. So anytime you see that when you run that intercept, you remember how you run it, maybe LR dot intercept, you put underscore. Do you remember that? Or you put LR dot coef and put underscore. This is the mathematics behind that your code.
So the regression table or this thing where you see error, you see intercept, you see
exactly.
Is it R1, R squared?
Exactly.
So it's all behind.
Yeah, this is also this is example of an algorithm.
Okay.
So do you understand this now? So anytime you hear an algorithm, this is the mathematics behind the algorithm. Do you understand this now?
So the ones with the P, you see P and
so those P are like looking at individual significance. Those P, they are looking at individual significance. So for example, if you are looking for the T, it is simply this your B1 divided by the standard error. That will give you the value of your T.
Okay.
Then you now have the P value of it, the corresponding P value to now check the significance of it.
Okay, I'm getting.
Are you getting it now? So
yes,
those codes we have been running. Import linear regression dot fit. You see that fit? You see when you say that dot fit, this is the algorithm behind it. So when you hear an algorithm, now do you know what it looks like now?
Yes, sir.
Because when we say it, we just imagine it that it's an algorithm. You don't understand, it's a mathematical step behind it.
So we can't run away from matrix.
Yes, you can't run. Now I told you that there are some basic things we are going to be seeing. But this is why you see, when you say you are a data scientist, a core data scientist, you see why you have to go back to the mathematics. This is the mathematics you need there. But the fact is that at this stage, yes, we are running these codes, isn't it? But the truth is that we may not appreciate what is going on at the back end. Okay, so that's why I will not say you must learn all of them, but at least just have an idea of what it looks like. Okay, so that you understand when to use them. So let's continue. So I'm sure this is clear now. So when you hear a regression algorithm, you understand what an algorithm looks like now, isn't it? Although we have to leave very soon, but let me just explain something here. You see, there's usually a challenge you have, right? Whenever you are running your model, you see sometimes, you know how we have run our dot, when we finish running maybe LR dot fit, isn't it? We now used to do a prediction, isn't it? They will now do a prediction. Do you remember that part?
Yes.
So when you do a prediction, when you do your prediction, two things can happen. When you do your prediction, two things can happen. Remember, what was your objective? Your objective was to minimize the error, isn't it? Your objective is to minimize the error, okay? But you see, when you are doing your prediction, two things can happen. Either it can lead to what they call overfitting. It can lead to overfitting, or it can lead to what they call what? Underfitting. I'm sure you have heard of this concept before. Overfitting and what?
Underfitting.
Underfitting. Okay. So when we say overfitting, what does overfitting mean? Overfitting. When you hear overfitting, what does it mean?
When the model has learned the data so much that it can give you like 100% accuracy.
Yes, you see, on that your trained data, you see, on that your trained data, on that trained data, when you bring anything close to that trained data set, because it has seen it before, it will be doing Yanga that I know you very well, isn't it? I know you very well because I've seen you before. So if we predict it so high, is it not? So it performs so well, the prediction performs so well on your training data. But when you try it on the test data, so there are two, there is not that your train and test. On the train data, it will predict it so well. On the test data, it performs what? Poorly. Can you see that? So you say your data is what? Your model is what? Over. Even if you bring a new data set, it will also perform what? Poorly. You say your model is what? Overfitting. Are we clear with that? But when you say your model is underfitting, when you talk about underfitting means that what? On your trained data, it performs poorly. On your test data or your new data, it also performs what? Poorly. We say your model is what? Underfitted. Your model is what?
Underfitted.
Because remember, your objective is to what? Minimize the error. But in this case, it's going to have what? High error. Okay. So in this case, when you say your model is overfitted, on the trained data set, it will what? Perform well. On the test data or the new data, it will perform badly. Underfitting means that what? On the trained data, it performs badly. On the test data, it also performs what? Badly. So your model is what? Fitted. So if this is the problem, what can you now do? What do you now do? If that is the problem, what do you now do?
You use more data or get new
Yes,
sets of.
you use more data, or isn't it? But you see, sometimes you can even use more data, and yet the problem is not there. So what do you now need to do?
You change the machine learning. Use another.
Yeah. So what you normally do again, you do what they refer to as what? Regularization. You do what they call regularization. Okay. And what you are simply doing there is just an extension of your linear programming. I mean your linear regression model. Okay. But in this case, what you are trying to do is to minimize that error. To minimize the error, especially the problem of what? Your bias and what? Your error of bias and what? Your variance. So to reduce this error of bias and variance, you see, because your model in your trained data set, it knows it, so it performs very high, is it not? So it becomes what? Biased. Can you see that? It becomes what? Biased. But when you give it a new data set, the variance is now very high, or the error is very what? High. So what do we want to do? We want to make sure it is unbiased and it is what? Has a what? No what? Error. So what they do is called what? Regularization. So to perform regularization, so what you now need? You now have another model to balance it, called what? Your ridge regression. That's when you now use what? Ridge regression, or you use what they call what? The lasso regression. Can you see how they are linked together now?
Yes, sir.
Yeah. So these are what they call hypertuning. They call it hypertuning. They call it hypertuning. Or you hear of hyperparameter tuning. Have you heard of that? Hypertuning. So
No.
you are tuning, so what they are saying, they are tuning what the model to what reduce the bias and reduce what the variance. So your ridge regression, this ridge regression helps you to overcome this problem of what? Overfitting. So ridge regression helps you to what? Overcome the problem of what? Overfitting. Okay? It will look at the trained data, predict it well. Look at your test data also and predict it also what? Very well. Okay? But there's a mathematics behind it, but I don't want to go into that mathematics. Okay? So you see, your lasso regression is just like a ridge regression. Okay? But what it helps you to do is to what? Help you achieve what they call your feature selection. Your feature selection. Your ridge regression helps you overcome the problem of what? This bias and variance, the overfitting problem, isn't it? So lasso regression, in addition to reducing what? The bias and variance or the overfitting problem, it also helps you what? In what? Feature what selection, choosing which is the most important variable. Remember your question about explainability, or how do I pick the variables?
Yes.
Okay, lasso regression also helps you do that. It helps you overcome the problem of overfitting and also help you what? Feature what selection. It will now pick, okay, this is now the best variables you should now what use. Okay, so any feature that has a very low slope or slope coefficient, it will eliminate the variable. So it will only pick what variables that are what? That which variables will you take? You only take variables that with high what coefficient that you can actually what explain it more logically. So that is about what? The lasso and ridge regression. So you see, from the problem of your linear regression, which may either be overfitting or underfitting, you now have to use another model called what? Ridge, which is what it does. What it does is actually regularization. How are you regularizing it? By ensuring your model is not biased and has what? Low what? Variance. That's your ridge regression. But in addition to feature selection, it will help you what? Take care of this problem of overfitting and also what? Eliminating variables with what? Low what? Coefficient, low slope coefficient. So it will now only pick variables that with what? High what? Coefficients that you can actually explain what is actually what happening. So that is it about the regression aspect. Because I have an engagement by 2:30, so I will need to leave. Okay. So by next week, when we come, I will explain the regression part, the classification aspect to it. Is that okay? So when you go back now, look at that any of the regression model now and try to understand how to calculate it manually. Because when you understand how it's done manually, when you see the model, when you're running those your codes, at least you understand what's happening at the back end. Is that clear?
Yes, sir.
All
Yes,
right.
sir.
So we'll meet next week, but keep practicing with your regression and your logistic regression. When we come back, I will explain other classification models for you.
Thank you
Okay.
so much, Dr. Francis.
Thank you,
All
sir.
right. That's
Thank
fine.
Thank you,
Because
sir.
I'm sure for some of us, this will be the first time we are seeing this type of nonsense, is it not?
Yes, so
Yes.
Yeah. Yes.
But this is actually what you need to understand, the whole framework of how you should think about it. Because
Well, we did that in university, so we're just
yes,
refreshing now.
yes, exactly. Because everything you are seeing here is what they actually. If you check your cargo, you will see all of them here. Everything you see in cargo, this is what you are seeing here. But it's just for you to understand why they are using which particular one. Okay, that's all you just need to do. Okay, so just keep practicing. So by next week again, we'll come and break down the theory. Because what I realize is that even when I show you how to do it, it looks simple, but sometimes you may not understand where it is going to, or how and why you are using it. So, but the foundation of every classification, every regression you are doing, it is based on this model we are seeing here. It's based on this algorithm. So all other algorithms now take their own from here. Every algorithm take their own feature from here. So once you understand, oh, this is what is going on at the back end. This is what an algorithm. Okay. So we'll see you next week. And if there's any public holiday, we can still use it. Otherwise, we'll see you next week.
thank
Is
you,
that
sir.
okay?
Thank you so much.
But the only thing next week, I don't know, can we do it by 12? Is it possible by 12?
Yes.
So we can have longer time.
Anyhow, sir.
We can discuss that one also on the WhatsApp
Yes,
chat before
okay.
next week.
All right, that's fine. So that we can have longer time, so I can cover most of these things. Eh?
Okay, sir.
All right, guys. See you next week.
Thank you,
Oh,
Doc.
All right.
Thank you, sir.
Guys. Enjoy the rest of your week.
Thank you, Doc.
All right. Bye.